So this is the final little part of kind of solving trig equations, and this is the last. This is just looking at the last few different types of trig equations that you might encounter and might obviously have to solve, and just how we deal with them. Okay, so we've dealt with substituting something in, substituting something out. We dealt with wave function, and this is just the last part, and it's still a trig equation, but it's just recognizing the form that we need to take to be able to solve it. So this is the same kind of idea as the last one, in the sense that we've got cos x's and we've got sin x's, and we can't substitute them out with anything useful. Okay, so we want to basically combine this into something that's just going to have the 1x, in which case we need to understand where this comes from. So this form, hopefully you can recognize, is an expansion of the ones that are in your formula sheet. So if you think of your cos a plus b's, your sine a minus b's, all of those different formulas, we can substitute them back out. So this is the expanded version, but if we substitute in the unexpanded version, then we can solve this. So it's just a case of recognizing the different form, and I guess that's what you've gone through with the last couple of examples, and this is no different. Okay, so hopefully you can spot this, and the fact we've got cos x cos 50, sin x sin 50, it should be ringing bells in your head, and you're thinking, right, that's like the expansions that I started with, in which case I want to substitute it back in. Obviously we've dealt with going one way quite a lot, and taking the cos of a plus b and expanding it, but we want to basically unexpand this. We want this in a more simple version, in which case we need to go back to the form in the formula sheet. Okay, so this version, and it's just a case of matching up with the right one. This is an expansion of the form cos of a plus b. So again, just be careful with the negatives and just be careful with everything. If you look at this, it's just in your formula sheet. Okay, you should see that cos a plus b is cos a cos b minus sine a sine b. And as long as you spot that, it's just a case of substituting it back into that version. Okay, in which case this is just the same as cos of x plus 50. And this version is a much easier version to work with and hence solve. Okay, we've only got one x now, we've only got one cos, much easier to solve, and we can just go ahead with, it's very similar to what we're doing in the last lesson in terms of the wave functions, in which case we're solving it for x plus 50 by finding the inverse cos of 0.5. Again, obviously because it's x plus 50, the interval changes. Again, the same as the last one, you can either change the interval and deal with it that way, or just think about what's happening at the end of it all. Okay. Either way, the related angle is going to be the inverse cos of 0.5. Again, it's an exact value, so it's 60 degrees. Okay, we're working in degrees, so that's fine. We're going to have a cast diagram, in which case because it's positive, it's going to be in the first and the last quadrant. So 0 plus 60 was 360 minus 60, but we're solving this for x, in which case we need to take away 50, in which case we get 10 or 250. Okay, so regardless of the fact that we changed the limit, change the interval, sorry, this doesn't actually affect the solutions that we find, okay? Which is why it's often not important to actually look at that until the very end, okay? It's entirely up to you, but you just got to ensure that when we find x, it is in the original limit, and obviously at this stage, 60 and 300, they were in the changed limit, okay? But either way, the answers are just 10 and 250. The main thing from this is just recognizing that form and basically unexpanding it, okay? Another type of example that you get is something like this. Okay, so you kind of get a proof at the start, in which case you get to show that, and then it's a hence solve. So this isn't necessarily anything in particular. This is not a particular version of anything that we've already looked at. It's just being able to deal with the left-hand side, making it look like the right-hand side. And then because it's a hence in the second part, it's basically using that right-hand side to solve the equation. Okay. So once again, we're kind of taking this version. We're just going to play around with it until such a point as it looks like 1 minus sine 2 theta. Okay, so we're not going to touch that. Don't do anything with that, but that's what you want this to look like. The reason the questions are done like this is that if you can't do part A, you can still do part B. Okay, so the idea is that hence solve the equation cos theta minus sine theta. That's just what we've got there. But the point is we change it out for 1 minus sine 2 theta, which is much easier to solve. The fact that we've got the 2 thetas here, okay, means it's very difficult to solve. Okay, you could do something in terms of wave function there, but the fact that it's squared is just that little more complicated. But we have readily available from part A something that's just 1 theta, and we can use that to solve part B. But nonetheless, in part A, we have to show that this equals that. So I'm going to take the cos theta minus sine theta all squared, and I'm going to do something with it. Right. Again, the fact that it's all squared, don't think this is the same as cos squared theta minus sine squared theta. If you have something like this, it's FOIL, in which case it's cos theta minus sine theta times by cos theta minus sine theta squared, so it's times by itself, in which case we have a FOIL situation, in which case we need to multiply it out. Okay, cos theta times by cos theta times by minus sine theta, and so on. So cos theta times by cos theta is cos squared theta. Cos theta times by minus sine theta is minus sine theta cos theta. And then minus sine theta times by cos theta is another minus sine theta cos theta. So we have two minus 2 cos theta sine thetas. And then minus sine theta times by minus sine theta is plus sine squared theta. Okay, if you need an extra line of working in there, then take it. Okay, but the bottom line is that is the same as that. Right, so dealing with this is a little bit more complicated, but hopefully there's a few things that you recognize in here. Okay, the 2 cos theta sine theta, okay, is, what am I doing first? Okay, so don't worry, we'll come back to that in a second, but I'm just rearranging this into the two parts. We've got cos squared theta plus sine theta squared theta minus the 2 cos theta sine theta. Right, cos squared theta plus sine squared theta is one of your trig identities from National 5, and we should know that cos squared theta plus sine squared theta, cos squared anything plus sine squared anything, is just equal to 1. So I'm going to substitute them out and make it a 1, and I still need to contend with this minus 2 cos theta sine theta. But the idea is that is just one of our double angle formulas. So again, it's from your formula sheet. The cos squared theta plus sine squared theta is not, though. That's from National 5, you have to memorize that one. Okay, but that one is just 1. This one is just one of your expansions. If you look at your formula sheet, you can see that 2 cos theta sine theta, or 2 sine theta cos theta, but it's just a bunch of things timed together, is just the same as sine 2 theta, which is exactly what we were looking to make it. Okay, so you don't have to do this whole left-hand side, right-hand side thing, but you have to basically start working on your left-hand side until such a point as it looks like your right-hand side. But it's 2 different expansions there, or 2 different identities that you need to know. One of them's in the formula sheet, okay, this one, but this one is not, so you need to know these ones. But again, it's just your trig identities, okay? So that allows us to do part B, okay? But again, if we couldn't do that, we can still do part B. As long as it says hence, if it's a show that question for part A, then you can use what you were supposed to find in part B, regardless of whether you actually found it yourself. So we're taking cos theta minus sine theta all squared equal to 1/2, and we're going to solve it for theta between 0 and 2 pi, okay? But the idea is that cos theta minus sine theta squared is just the same as 1 minus sine 2 theta, in which case that is equal to 1/2 as well, and we can solve that equation much easier, okay? So this is between, because we're not solving it for theta, we don't have theta, we have 2 theta, in which case 2 theta is between 0 and 4 pi. Again, you can deal with that now, or you can deal with it later, whatever you choose. But in terms of solving it, okay, we're going to take away 1 from both sides, in which case it's going to be minus sine 2 theta equals minus 1/2. And if minus sine 2 theta equals minus 1/2, then positive sine 2 theta will equal positive 1/2. Okay, lots of ways you can do that. I've probably missed out a line of working that you'd probably want to put in there. If you added sine 2 theta to both sides and then took away 1/2, either way you get this stage, okay, but you probably want an extra line of working in there. But it's just purely, I've taken away 1, and 1/2 take away 1 is minus 1/2, leaving with minus sine 2 theta on this side, minus 1/2 on this side, and then I can change it by multiplying through by -1 to sine 2 theta equals 1/2. Once you get to this stage, it's just a case of doing the inverse sine of 1/2, but remember we're finding the related angle before we find our 2 theta. So the related angle is the inverse sine of 1/2, which is 30 degrees, or pi over 6. It has to be pi over 6 because we're solving this in terms of radians, so we do need to look at that, we do need to change it. Whether you change it now at the end is entirely up to you. But in terms of our 2 theta, okay, it's going to be in the quadrants that are positive for sine, so A and S. Okay, and in the next stage we find 2 theta. Okay, bearing in mind that with 2 theta has is between 0 and 4 pi, sorry. So 2 theta will equal in the first quadrant 0 plus pi over 6, in the second quadrant pi minus pi over 6, and then we're back round again because we're going up to 4 pi, so it'll be 360 or 2 pi plus pi over 6, and in this one it would be 3 pi minus pi over 6. Okay, as I say, if you dealt with that in terms of degrees first, it would be 0 plus 30, 180 minus 30, 360 plus 30, and 540 minus 30, and then change it back into radians at the very, very end. Okay, but simplify them, and you get these, and then we need to divide by 2 at the end, giving us 4 answers. So pi over 6 divided by 2 is basically pi over 6, pi over 6 times by 2. So pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. Okay.